So we imagine we could get y by itself. Could we get y by itself on this one? Yeah, we could just square root both sides. We get two equations for y, one with a plus sign, one with a negative sign, if we square rooted both sides. Okay? But we don't want to do that. We want to do our derivative with implicit differentiation. So we take the derivative with respect to x of the left side, and we take the derivative with respect to x of the right side. The right side is the easy one, because what's the derivative of tan? Are your shortcuts coming? Have you been practicing them? Or did you take the weekend off? Secant squared. Keep the inside the same. This would be a chain rule multiplied by 7. On the left side, you take the derivative like you would normally. If you had y squared, the derivative would be power rule 2y. But then we have to multiply by a y prime or a dy dx. This time I used y prime as a notation just because it had it in the question. Then to get the y prime by itself, you just have to divide both sides by 2y. So we do all of our derivative rules like normal, but whenever you're doing the derivative of something with a y, you have to think there would be a chain rule after the fact, and you'd have a dy dx or a y prime in the end. So we take the derivative with respect to x of both sides. Shortcut rules. Let's do the right side first. What is the derivative of e to the x? E to the x. That part is easy. Oops, I showed too much of the other side. Here, do you see you have a chain rule? A big chain rule. You have the tan inside of the squared. You have the y inside of the tan. So, outside first. The derivative of the exponent, the 2 would come out in front. Keep the inside the same. Multiply by the derivative of the inside. What's the derivative of tan? Secant squared. Keep the inside the same. Then what's the derivative of y? The derivative of y. And now to solve for y prime, we just need to get this by itself. So we can divide both sides by the 2 tan y secant squared y. Could you get y by itself on this one? First you'd have to square root both sides. Then you'd have to do tan inverse. It would be possible to get y by itself, but it wouldn't be very nice. And it would be, and of course it would involve the derivative of an inverse function, which, if you look, that's coming on page 16. X squared minus y squared equals 25. This is a hyperbola. If you don't know how to graph hyperbolas, you can look them up. It used to be part of the grade 12, graphing hyperbolas. But they took it out. It's not super hard. But this would make a hyperbola. If you wanted to find y double prime, well, first you'd have to find y prime. So we take d dx of everything. Well, d dx of x squared will just be 2x. d dx of y squared will be 2y, but then because of the y, you'd have to include a dy dx, or y prime. And what is the derivative of 25? 0. So we do all of the terms with just x's like normal. When we do the derivative of y squared, We would do the outside function, 2 comes out in front, keep the inside the same, but then you have to do a chain rule and multiply by the derivative of the inside. So any term with a y, your very last step is always you're going to multiply by y prime, or multiply by dy dx. Now, can I get y prime by itself? Absolutely. Y prime is x over y. So how would we find the second derivative? Well, we could use the quotient rule. Keep the bottom the same, derivative of the top. Keep the top the same. The derivative of the bottom would be 1, but then you'd still have to have a y prime after that because of the chain rule over the bottom squared. And then, where the y prime is, you can substitute in an x over y. If we wanted to, we could simplify this even further. So we'll do this one together, and then I'm going to let you try the last one on your own. So we want to find the equation of a tangent line. We have seen lots of questions that have started this way. Find the equation of a tangent line. What are you going to need to find an equation of a line? A point and a slope. How are you going to get the slope? From the derivative. How are you going to get the point? Well, sometimes they're so nice they tell you. Otherwise, sometimes you have to plug it into the original equation. So, I have the point, I need the slope. How do I find the slope? I need the derivative, so I need to do implicit differentiation here. I take d dx of everything. d dx of x squared is 2x. d dx of 2y squared would be 4y, but then because it has a y, I'd have a dy dx. And d dx of 4y will just be 4, but then because it has a y, I'd have a dy dx. I need to solve for dy dx. This time I have two terms with dy dx. I will get those all on the same side of my equation. And then I can factor out the dy dx, which allows me to get it by itself. 2x over 4 minus 4y, or you could simplify it. Then at that point, if I plug in root 2 and 1, it is undefined. It causes me to divide by 0. If a slope of a line is undefined, what's happening? Straight up and down? So you have a line x equals root 2. Technically, graphically, not graphing perfectly to scale, but an ellipse looks like a flattened circle. The point they chose was one of these on the end, so that the tangent line went straight up and down. That's the only way the tangent or the slope would be undefined. Tricky, because at this point when you got undefined, chances are you'd be like, like you do that little laugh like, I don't know what to do next because you wouldn't know what to do next, right? Kind of laugh. This is a tricky question because we have to think, well, this is my ellipse. The only way that it would be undefined is if your slope was straight up and down, because then there's no run. And how do I write vertical lines? Vertical lines are x equals, and I know the x coordinate because I know that this point was at root 2 comma 1. So then my only line is straight up and down, x equals root 2. That's why this was a good one to do together, rather than say, hey, try this one on your own. But the next one, try that one. I'll put up the answer in a bit. How you did. Oh, it was on the other side. I drew a picture. Did you take the derivative to find your slope? And when you rearranged your equation, this is what dy dx ended up being. 1 plus e to the y times sine x over cos x e to the y. If you want to find dy dx at 0, 0, you plug in 0 for x and 0 for y, and this is not bad. You get 1. Which means the slope of your normal is 1 over negative 1. And you have your point. So you can get your equation of your line.